Yes, sir.
Okay, so do you have any doubts from the previous chapters that we have studied?
No, sir.
Okay, so today we are going to start our haloalkane chapter. So first of all, please like open your front camera, then we can start. Okay, see, the name of the chapter is haloalkanes and haloarenes, right? So we will start with what is haloalkanes first of all, right? We can call them haloalkane or we can call them alkyl halide. Both of these things have same meaning. If we are talking about haloalkanes or alkyl halide, we are doing what? We are just replacing, this is our alkane, right? If we have to be specific, this is methane. If I add hydrogens here, this is methane, right?
Yes,
Methane is
sir.
an alkane. Now what we are doing is, we are just replacing one hydrogen from an alkane and introducing a X. This X is halogen.
Halogen. Yes, sir.
And these compound are haloalkanes, right?
Yes,
So
sir.
what are halogens?
Sir, chlorine, bromine, iodine.
Great. Chlorine, chlorine, bromine, iodine, basically group 17 elements.
Yes, sir.
Now, before going into the chapter, or this is in your NCERT, so I will consider it as a chapter as well. So let us talk about the application of haloalkanes, right? Where we are using this chapter. So this has very prominent use in medicinal chemistry, right? The drugs that we are consuming have a great contribution by the haloalkane compound. For example, there is a drug called chloramphenicol, right? This chloramphenicol drug is used to treat typhoid, and this drug basically look like this. You don't have to learn the structure, just a general knowledge, right? This drug is formed by the haloalkanes, the starting reagents or intermediates that are uh, the reason that we are getting this product are haloalkanes. So haloalkane is basically used for creating drugs, medicinal chemistry, right? For example, if we talk about malaria, malaria is a very like serious disease, right? So for this we use a medicine called chloroquine, and this chloroquine structure look like this. And again, this is formed by the contribution of haloalkanes. Here you must be seeing this chlorine part, right? This is a halogen. This is a halogen containing compound. So this is formed by a haloalkane. There were some starting reagents with the help of which we are able to produce this drug. So haloalkane is very important, right?
Sir.
One more example, right? Anesthetic drugs. Nowadays we are using halothane. Halothane is an anesthetic drug that is used to numb the pain, right? Whenever you are doing some surgeries, right? Doctor used to give you doctor gives you halothane basically to numb the pain that is caused due to the surgery, right? So the halothane again is a compound which have haloalkane, right? Halothane consists of halogens and alkanes, right?
Yes, sir.
In the like before halothane, we were using chloroform. You must have heard in serials they show if you put someone put a chloroform cloth into someone's face, they will just what? They will do what? They will just what we call that? What's the specific word for that? Behosh hona.
Sir, they will,
Okay,
they
वो
will get
बेहोश हो जाएंगे.
unconscious, I think.
Unconscious. Good. Unconscious, right? So
Yes.
chloroform is not used anymore. Why? Because chloroform was found to be toxic and carcinogenic. If you use chloroform, then you have some chances of getting heart diseases. Carcinogenic means heart diseases, right? So chloroform is not used anymore. We are using halothane instead of chloroform, right? And chloroform is basically what? A haloalkane. Why a haloalkane?
Yes.
Because the formula is simple CHCl3. A haloalkane, right?
Sir.
In World War One, 85% casualties are due to the poisonous gas, this phosgene. In World War One, 85% of the casualties were due to this phosgene gas, and this phosgene gas is formed with the help of haloalkanes, right? This phosgene gas made the soldiers blind. Just by inhaling some amount of it, the soldiers went blind. So this is again formed due to haloalkanes, right?
Yes,
They
sir.
are also used in pesticides. Example is DDT. The structure look like this. So haloalkanes have very prominent use in like most industries, right? Wherever you look at, you are using haloalkane in some part. So now we will talk about how we can classify haloalkanes, right?
Yes.
So on the basis of primary, or you can say 1 degree, 2 degree, 3 degree carbons. Have you heard about it? This is the 11th concept. Have you heard
Sir.
about primary, secondary, and tertiary? Okay.
Sir.
So, so if our halogen is connected to a carbon and that carbon is only connected to one carbon, that this is 1 degree carbon, right? And this whole compound is 1 degree alkyl halide or 1 degree haloalkane, right? If we look
Sir.
at this compound, this is the carbon which is directly connected to our halogen, right? And to this carbon, we have how many carbons which is directly connected to this? The one that I've two. So this is 2 degree alkyl halide. Similarly, this is 3 degree alkyl halide. Is it simple? This is very
Sir.
basic. Okay. Now, this allylic position. On the basis of allylic position, we can also differentiate between haloalkanes. Do you know what is allylic position?
Also.
Okay. The allylic position is the position which is next to the double bonded carbon. This is a double bonded carbon, right?
Yes,
To
sir.
the next position, of this double bonded carbon, if we have a halogen, if to the next carbon of the double bonded carbon, we are having a halogen which is directly connected to this carbon, this highlighted carbon, then this position is allylic position, right?
Sir.
Is this clear? So
Yes, sir.
we will again talk about 1 degree, 2 degree, and 3 degree allylic position. For example, this is our double bonded carbons, right? This carbon and this carbon is in the double bond. To the next carbon, which is directly attached to this alkene, this is the carbon, and to this carbon we have a halogen. So this carbon is allylic carbon, right? The carbon next to the double bonded carbon having a halogen directly attached to it is allylic position, right?
Yes, sir.
How we are saying this is 1 degree allylic position. Now we know which is allylic position, but why we are putting it into the category of 1 degree?
Sir, because it is attached to only one carbon.
Good, good, good. Similarly, this is 2 degree allylic position and this is 3 degree allylic position. I hope this is clear.
Yes, sir.
Now, we have another thing which is benzylic position. If you are seeing a group like this, where we are seeing a benzene and a methyl group, and this is attached to a main chain as a side group, then we will call this group benzyl group, right? Suppose we have a main chain, this is our main chain, and this group is attached as a branch. So we will call this benzyl. Okay.
Yes, sir.
So again, we will do what? 1 degree, 2 degree, and 3 degree benzylic position. This is our benzylic position. And to this carbon, we have only one carbon which is directly attached. So we will call it 1 degree. This is 2 degree and this is 3 degree. Is it clear?
Yes, sir.
One important thing that I would like to uh, like highlight here is in all of these like classification, the carbon should be what? sp3 hybridized. In primary, allylic, benzylic, the carbon should be sp3 hybridized. You can calculate the hybridization, right? If I am drawing it like this, You know, na, we don't show the hydrogens. Like it is understood that hydrogens are like this here.
Yes,
We
sir.
don't show hydrogen in this bond type of structures. So if you have to calculate the hybridization of this carbon, then what should be the hybridization? sp3,
Yes, sir.
right? Here, what should be the hybridization? sp3, and again here sp3. How can you calculate the hybridization? Do you know the formula for that?
Yes, sir.
Okay, see, just note it down somewhere. It is very important. The formula to calculate hybridization is sigma bond, number of sigma bonds plus free lone pair. This is the formula to calculate hybridization, right? Okay.
Yes, sir.
Now, let me give you an example so this concept gets clear. Suppose I am writing this and I am writing this. You have to tell me the hybridization of this carbon and this carbon. The one that I've highlighted, you have to tell me the hybridization of these two carbons.
The first one is sp3 hybridized.
Okay,
The second one
how?
is sp2.
How?
That because it has single bonds.
In S here we have single bonds, but are you applying the formula? Because I think you are just using your like memory stuff. You are seeing double bond and you are putting it into sp2 category, right? Have you
Yes,
used the
sir.
formula here? Try to use the formula, otherwise you won't be able to solve the complex questions. See, suppose here we have two hydrogens, right? Two
Yes, sir.
hydrogens here.
Yes, sir.
I can draw this these hydrogens like this. Now tell me how many sigma bonds is this carbon having? Four sigma bond or not? One sigma
Yes, sir.
bond, two sigma bond, three sigma bond, four sigma bond. If I have to calculate hybridization, I will calculate what? Sigma bond plus free lone pair. Here we are not talking about lone pair, so we will not include that. So how many sigma bonds do we have for this?
4.
Four. If I am having the value 4, then I will say what? For S subshell, how many orbitals do I have? For S subshell, we have only one orbital, so I will include only S subshell. For P, how many maximum orbitals I can use? 3.
3.
So due to this, I have sp3. 1 from S and the 3 for P3, right?
Yes, sir.
Now, if we talk about this one, I can write the hydrogen in this way. If you have to calculate the sigma bonds for this carbon now, tell me how many sigma bonds is a carbon having?
3.
How? 1,
Sir,
2,
1. Yeah. 3.
and this is 5. Okay,
Yes,
hence this is sp2. Right?
sir.
That was about hybridization. Now, we will talk about a new category, this vinylic halide or aryl halide. So, for vinyl halide, it is similar to allylic position but is different. In allylic, what we were seeing that the halogen is attached to the carbon which is next to the double bond.
Yes,
The
sir.
halogen was attached to this carbon. This is allylic. But if the halogen is directly attached to this double bonded carbon like this, then we will call this position vinylic position, right? We are going to use these naming stuff in the reaction, so try to understand it. If you have doubts, you can ask. This is vinylic. Why? Because to the double bonded carbon, we have directly attached a halogen. Okay, this basically look like this. And this carbon is sp2 hybridized, and this is vinylic carbon. This carbon is vinylic carbon. Okay,
Sir.
is okay. Now, if we have a halogen which is directly attached to a ring, benzene type ring, right? So we will call this position aryl. This is aryl halide. Okay, I will
Yes, sir.
like we will talk about in detail what are aryl halides or haloarenes. Once we complete this, I will just give you a brief between, like I will give you a data about how haloalkenes and haloarenes are different. For example, we are going to talk about these two terms in this entire chapter: haloalkane and haloarenes. Right? We also call it alkyl halide and this thing aryl halide. So what's the difference between these two things? When we are talking about haloalkane or aryl halide, then we are basically talking in terms of open chain. If I am having a open chain like halogen containing species, a open chain halogen containing species with a alkane with a single bond, then I will call it haloalkane or halide, aryl halide. But if I am having a ring type of structure, then I will call it haloarenes. A ring type structure with a double bond, I will call it haloarenes or aryl halide. Okay, we will talk about
Yes,
them
sir.
in details as we continue with the chapter. Now, one more thing before we jump to the preparation part: degree of unsaturation. This is again 11th concept. Have you heard about this term, degree of unsaturation?
Yes, sir.
Okay. So basically, alkene and alkynes are unsaturated compound. Have you like we call
Yes,
them
sir.
unsaturated compounds. Alkenes and alkynes are unsaturated compound, and alkanes are saturated compound. Why we are saying this? Because in alkenes, we are giving the maximum number of hydrogen that a carbon can contain. For example, carbon has the capability of forming only four bonds, right? Carbon can form only four bonds. And here we are placing our hydrogen in this way. I am talking about this ethane. Here I am giving the maximum number of hydrogens that a carbon can contain here, because carbon can make maximum number of four bonds that it is doing here. But if I am drawing this alkene structure here, due to this double bond, we are giving it lesser number of hydrogens. Here we were giving a single carbon three hydrogens. Here we are giving only two hydrogens.
Two hydrogen.
The loss of hydrogens from alkane to alkene is how much?
One for each carbon.
Two total hydrogens,
So
right?
two. Yes, sir.
So if we are losing two hydrogens and converting alkane to alkene, this is what? Degree of unsaturation. We are creating unsaturation, right? What is the basic meaning of unsaturation? Unsaturation means you are having lesser number of anything, a lesser number of particles or anything that you are capable of holding. Suppose you are capable of holding 10 balls, right? The
Yes, sir.
maximum number of the balls that you can hold at a single time is 10. So if you are holding the 10 balls at the same time, that you have reached your saturation level. You cannot hold any more balls, right? But somehow
Yes,
you are
sir.
holding only 5 balls. Then you are unsaturated. You can still hold some more hydrogens or more balls, right? So this is what unsaturation. And if you are going from saturated to unsaturated, saturated alkene, then we will call it degree of unsaturation. Okay.
Yes, sir.
Now, if we are losing two hydrogens, then the degree of unsaturation will be 1. Okay. If I look at this specific example, from here to here, we have lost two hydrogen. So the degree of unsaturation is 1.
Yes, sir.
Okay. Now, to alkene to alkyne. From alkene to alkyne, how many hydrogens are we again losing? Two hydrogens.
Two.
So from here to here, again, the degree of unsaturation is.
One.
But if I am going directly from alkane to alkyne, sorry, then how many hydrogens I am losing?
Two.
Total,
Oh,
total, from
four. Four.
four. So the degree of unsaturation will be 2.
2.
Okay. This is what about degree of unsaturation, and we are going to see its significance, like how it is related to our chapter. So for that, just give me a second. Degree of unsaturation in simple terms means number of pi bonds and rings. Degree of unsaturation tells us whether a compound, suppose we are having a molecular formula C6H5O2, right? Degree of unsaturation tells us how many types of or what possible structures from this molecular formula we can form. If degree of unsaturation is 0, we will see there are no possibilities of pi bonds or rings. Okay, if degree of unsaturation is 1, then there might be some pi bonds, there might be some rings, there might be some combination of it, right? So in simple terms, we can call degree of unsaturation is number of pi bonds and rings. And the formula to calculate degree of unsaturation is this. This C is carbon. Okay, C plus 1 minus bracket H plus X, H is hydrogen, X is halogen, minus nitrogen divided by 2. If in your molecular formula, you have been given oxygen or sulfur, you will ignore this, right?
Yes, sir.
With the help of this formula, you can calculate degree of unsaturation for any molecular formula. If we take a specific example, look at this. This is a molecular formula, right? With the help of which we can create several structures, right? You must have heard in isomerism. What is isomerism basically? Where we have single molecular formula but different structures, right?
Yes, sir.
So this single molecular formula can form several structures, several different compounds, right?
Yes, sir.
So first of all, how can you calculate the degree of unsaturation for this? How many carbons do we have? 4.
4.
How many hydrogens?
6.
And 1 nitrogen. We have oxygen, right? But we are supposed to ignore it. We have to ignore oxygen or sulfur. So if I put the values, I will get degree of unsaturation 2. So what does this mean? If I am having degree of unsaturation 2, what does this signifies? It means our our molecular formula could create a compound which can contain 2 pi bonds. Suppose this is our, or let me draw it like this. We have a 4 carbon chain, right? If I am
Yes,
getting
sir.
degree of unsaturation 2, it means it could have 2 pi bonds, it could have 2 rings, it could have 1 pi bond or 1 ring combination as well. So suppose I have 4 carbon main chain. Degree of unsaturation 2 means it is either going to have 2 double bonds like this in its structure, right? In its structure, it is either going to have 2 double bonds like this, and the respective atoms will occupy some specific space. Or what it can do, it can form a ring. Okay. Or what else it
Yes,
can
sir.
do? It can form a ring plus pi bond. So the higher the degree of unsaturation value you are getting, the more complexity you are observing while drawing the structures. So whenever you have asked to draw isomers, you will first calculate the degree of unsaturation. If your degree of unsaturation is 0, that means you are not going to get any rings or pi bonds while you are drawing the structure. Okay, so degree of unsaturation is very important before doing or like drawing any isomers. So is this clear, or
Yes, sir.
like I think, are you sure this is clear?
Yes, sir.
Okay. So this is a question from your NCRT. They're asking draw the structure of all the 8 structure isomers. They have specified from this molecular formula, you are going to get 8 structural isomers, 8 different structural isomers, right? And you have to also give the IUPAC naming for them and classify them as primary, secondary, and tertiary, right? So first step to draw the isomer is to calculate degree of unsaturation. So if you calculate the degree of unsaturation for this molecular formula, how or what value we are going to get? First of all, what's the formula for this? C plus 1 H minus X plus N divided by 2.
Minus X. Yes, sir, but there is no N, so we have to leave it, right?
Yeah, we have to leave it. Good. How many carbons do we have here?
5.
So this is going to be 6, right? Uh,
Yes, sir.
we have 11 hydrogens and how many halogens?
1. No.
1
Yes, sir. 1.
divided by 2.
Divided by 2.
6. Okay, we have to do what? Let me check the formula. H plus x minus n. Right. So this is going to be 6 and degree of unsaturation is 0.
0.
So if the degree of unsaturation is 0, that means in our various isomers, a molecular formula can give a certain number of isomers, right? In those isomers, we are neither going to have a possibility where it could have pi bond. We are neither going to have a possibility it could have a ring. So we are going to exclude the possibility of having rings or pi bonds. The only thing that we are going to get due to the degree of unsaturation 0 is a chain, and that too a alkane chain. No alkene, no ring, only alkane chain. So this is making our task very simple, right? No pi bonds and
Yes,
no
sir.
rings. Now, how to approach or how to start the like how to form these structures. So you have to start with the longest chain. First of all, the maximum number of carbon that we are having here is 5, right? So we will start with the carbon chain of 5 member, like 5 member carbon chain. Our main chain is going to have 5 carbons, right?
Yes, sir.
Then we have to assign a bromine. Do you know if we are having the IUPAC name which is same? Like suppose I am drawing a compound like this. I am taking this. I have just assigned this bromine here. Are these two compounds different or same?
They are same.
Why?
Sir, because its naming will be the same.
Good, good, good. Now, what we can do? First of all, the maximum number of like the biggest chain that we can make is pentane, right? We will form pentane and we will try to make combinations. The first case is I can put the bromine here on the first carbon, right?
Yes, sir.
So what is the name for this compound? What should be the name? Do you know the IUPAC?
Yes, sir.
Okay, so
Sir,
try to
bromohexane.
do we have a 6-member carbon chain?
Sir,
See,
bromopentane.
good. 1, 2, 3, 4, 5. This is okay. What else we can do? We can put this bromine on the carbon number 2, right? We will have a different isomer. So here the name should be what for the second one?
Bromopentane.
2-bromopentane. Good. What about this one? 3-bromopentane, right?
Sir.
Now a question. See, I can make these 3 possible structure with the pentane chain. Is there a possibility where I can form some different isomers or not? Suppose if I am doing this, I am again shifting our bromine here. Is this going to give me a new structure, new isomer? I have
No,
to
sir.
just change the position of bromine. Why? Because
Sir,
this and this is same
yes, it is the same.
now. So from the pentane, from 5 carbon chain, we cannot make any more isomers, right? We have to go to the next chain. After 5, what we can do? We can make the main chain of 4 member or 4 carbon chain, right? Our main chain, we can reduce it from 5 to 4. How we are going to do this? This is my main chain and I have added one methyl group as a branch. What I did? I converted this main 5 carbon chain. I converted pentane to butane. Why? Because in isomers, we can have any number of possibilities. We can change the position of any atom, but it should give us a different structure, right?
Yes,
The
sir.
name should not be same. So here what we are doing, we have just placed a methyl group as a branch. So what should be the name of this compound?
Bromo
Okay,
bromo 2 methyl pentane.
okay. Butane, not pentane, because the main chain is consisting of four carbon. This is a group. The main chain is having four carbon, and for four carbon we use butane. Is
Butane.
it clear?
Yes, sir. Yes, sir.
Okay, what about this one? Here you can do the
3
numbering
bro.
from. Okay, tell me first, tell me.
How long? 2 bromo 2 methyl butane.
Good. You can do the numbering from here, like this, 1, 2, 3, 4, or you can do the numbering from here as well. The outcome is going to be the same.
Yes, sir.
2 bromo, 2 methyl. What about this one?
Bromo 3 methyl butane.
Good. What about this one, last one?
Bromo 3 methyl butane.
Now, is there any other possible way where we can draw a new structure, a new isomer with a carbon having four carbon as main chain? Can we draw any other isomers as well
Yes, sir.
with the help of this? Try to imagine it. I might have not drawn all the structures. Try to imagine, like, try to see whether after like changing the position of this methyl or bromine, is there a possibility we can get some other isomer with a different name, but the main chain should be butane.
Sir, 3 bromo 2 methyl butane.
You are saying 3-bromo 2-methyl butane. Okay. For this, you are saying you have placed the bromine here and methyl here, right?
Sir.
Try to think about it. Whenever we are going to name a compound as per IUPAC, we have to do the numbering from the side where the lowest locant are observing. If I am going from here, out of methyl or bromine, which is higher priority group,
Mm.
so we are always going to do the numbering in this way. Is in this way, the bromine will always be at the second position if we are drawing a structure like this. The possibility of getting 2-methyl 3-bromo is not valid. That compound is not valid. The name is not valid, right? If you are drawing it like this, you are always going to write 2-bromo 3-methyl. Okay, so here there are no further possibilities to draw isomers with a butane chain. So now we will do what? We will again uh, shorten our main chain from butane to propane. Now our main chain is how many carbons? Like consisting how many carbons?
3.
This is our main chain, right?
Yes,
Here,
sir.
if I have to draw it in a different way, how can I write it? Just give me a second. This is nothing but this. See, CH3, C, CH3, 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 and Br. So what should be the name of this compound?
Bromo
First of all,
3
okay,
dimethyl propane.
see, 1, 2, not 3. Bromo
Bromo
2,
2 dimethyl
yes.
propane.
2 comma 2 dimethyl propane, right? Is there
Yes,
any
sir.
possibility where we can get a different isomer? You can do
sir.
one thing here. You can either place this bromine here, right? If you are doing this, suppose you are removing this bromine from here and you are attaching it here. And if you are removing here, attaching here. In every case, the name of the compound is going to be the same, right? If you
Yes,
are
sir.
placing bromine here or here, the name of the compound is going to be same because these methyl groups are identical. No matter where you will attach the bromine, the compound is going to be the same. So the only possibility from propane chain is one isomer. So how many total isomers are we having now?
8
So this is your answer. The last part is you have to identify the 1 degree, 2 degree and 3 degree. This is 1 degree or 2 degree carbon. This is 1 degree or 2 degree halide, alkyl halide basically.
degree.
Which one?
1 degree.
This is 1 degree. What about this?
Degree.
What? 3 degree?
Sir, degree. 2 degree.
2 degree. Okay. What about this one?
2 degree.
2 degree. Good. Okay. What about this one?
1 degree.
Okay. This,
2 degree.
this one.
3 degree.
Good. This one. 1 degree, right?
1 degree. Yes, sir.
What about this one?
Sir, 1 degree.
Good. So this is your complete answer. You have drawn all the isomers, you have named them, and you have also write the 1 degree, 2 degree, or 3 degree one. Right.
Yes, sir.
Now we will move ahead and we will talk about the reason. The reaction that are happening in haloalkanes are due to the nature of CX bond. Due to the polarity induced due to the electronegativity. Suppose if we are talking about this CX, this is carbon, this is halogen, right? Out of
Yes, sir.
carbon and halogen, uh, halogens electronegativity is more. Halogens are more electronegative than carbon. So what it is doing to the whole compound is, suppose ideally they have like, first of all they have contributed one electron each to make this bond, right? One electron from the carbon and one electron from the halogen, so that they can make the bond. But due to the electronegative nature of halogen, what it is doing, ideally the electron should have been placed like this. The halogen electron should be near to the halogen and carbon's electron should be near to the carbon, right? Because they are making a type of covalent bond. In covalent bond, equal number of electrons are shared to make a bond, right? But due to its electronegative nature, what it is doing, it is pulling both of these electrons towards itself. The electrons which were supposed to be equally shared, the halogen, due to its electronegative nature, it is pulling those electrons towards itself, slightly like in its direction. So the electron density is slightly shifted towards halogen, right?
Yes, sir.
Due to it, halogen is bearing this partial negative charge. What is partial negative charge? The partial negative charge is the charge which is due to the electronegative nature. In whenever we are using this partial term, we are not actually breaking the bond. Okay, let me see. Suppose if you are doing this partial sign, that means you are not breaking the bond. This partial charge is just due to the electronegativity. But on the other hand, if you are writing it like this, X and negative, if you are writing like this, that means you have broken the bond. Suppose here, ideally the electron should have been like this because this halogen is greedy and it is trying to pull the electrons towards itself. So the overall electron is carrying a negative charge, and both of the electron is near to the halogen. So here it is bearing a partial negative charge, right?
Yes, sir.
But if you are breaking this bond, suppose by some reaction you have broken this bond, so after the breaking, it will bear the complete positive and negative charge respectively, right? After breaking of bond, we are placing the complete positive or negative charge, but if we are not breaking the bond, then we will use these partial terms. Is this clear?
Yes, sir.
Now, whenever there is a charge separation, there will be a dipole. What is dipole? Dipole is basically from low charge to high charge, low density to high density. Halogen is bearing negative charge, right? So the dipole moment or dipole direction will be from carbon to halogen. This is our net dipole. And because of this polar nature, because of this polarity due to electronegativity, these haloalkenes are prone to various reactions. The things that we have studied in the in the application part now, how we are forming those chemicals, how we are forming those medicines. We are forming those medicines because they have this partial negativity. Due to this partial negativity only, other things are attacking at carbon or halogen, right?
Yes,
So
sir.
due to this electronegativity, everything is happening. This is the reason why we are getting different product, right? If there were no polarity, we won't be able to see much of the reaction here. Now, what is dipole moment? Dipole moment is denoted by mu, and it is nothing but charge into distance or displacement. Suppose this halogen have some charge, some negative charge, right? And it is separated by a certain distance. This is distance. So if you multiply the charge on halogen by this distance, what you are going to get?
Dipole.
Dipole moment, and it is denoted by debye. Is this clear? What is dipole moment?
Yes, sir.
Dipole moment is the net charge, what you can say, net charge displacement from a less electronegative to higher electronegative element, where we will show the dipole from low density to high density. And this dipole moment is nothing but charge into displacement. Charge on the negative atom into the distance that it is separated by other atom, right?
Yes, sir.
Now, have you heard about nucleophile or electrophile?
Yes, sir.
This is again, okay, good. What is a nucleophile then?
Sir, sir, they like positive charges.
They like positive charge, good. So they should be having some negative charge, right? Because negative charge will attract positive charge, is it not?
Yes, sir.
So we can say electrons are nucleophiles are what? Electron-rich species.
Yes, sir.
For example, if you are a nucleophile and you have given a choice, either you can attack on carbon or halogen. Which side you are going to attack and why?
Carbon because they attract opposite charges.
Because carbon is having a partial positive charge, right? So this
Yes, sir.
charge separation is the reason why the nucleophile is attacking, and the nucleophile is attacking and creating new compounds. So this is the reason of entire chemical reaction. Now, from this table, there is a question that we will like to understand here. Suppose if you look at this data, these are halogens, fluorine, chlorine, bromine, iodine, right?
Yes, sir.
If I am talking about CX4, in CX4, we have same atom at every side. So here what we will see, equal and opposite dipole cancel each other out. Have you heard about this? It is a 11th concept again in
Yes,
organic
sir.
chemistry. Equal and opposite dipole do what? If you don't know this, I will teach you. Just
They
don't,
cancel each other.
you know about this concept, right?
Yes, sir.
Okay. So that's why the dipole moment for CX4 is 0. The dipole moment is CF4, CCl4, CBr4, and Ci4 is 0, because the dipole moments are equal and opposite to each other and they are cancelling each other out. Okay. But
Yes, sir.
if we have a compound like this, CHF3, for example, if you are having CHF3, if you are having CHCl3 and so on, then there should be some certain dipole moment. For example, if I am drawing it like this, Cl, Cl, Cl and H. So the dipole moment should be somewhere around here, right? So basically it will have some dipole moment in some certain direction. So what we are observing here is the dipole moment is decreasing down the group as I am going from CHF3 to CHI3. The dipole moment is
increasing down the group.
Y, because the charge on fluorine is higher than charge on iodine. As we are moving down the group, the charge is decreasing. And if the charge is decreasing, the dipole moment should also.
Decrease.
So because fluorine has high charge, because it is very small and it has high charge density, or we can say fluorine is the most electronegative element, is it not? Fluorine is the most
Yes, sir.
electronegative element. So the tendency of it to pull the electron density from other atom will be highest. So if it is pulling the electron density from other species, then it is having the highest charge on itself, right?
Yes, sir.
So we all observe the trend here. The same trend will be here, but the question will come from here, right? Here what you can see, as we are moving down the group, the ideal order should be what? As we are moving down the group, the dipole moment should decrease. But here we are observing some anomaly. From CH3F and CH3Cl, the order should be the dipole moment of CH3Cl should be lesser in comparison to CH3F, but it is higher. They will ask you the question, why is this happening, right? So can you guess it, like what should be the case?
Sir, Wonder Walls force.
No.
Sir,
Mhm.
atom size.
You can say that, but that's not the entire reason. For this, you have to look at this formula carefully. Here, we have two factors that are contributing. First one is charge, but displacement is also contributing, right?
Sir.
I accept that. Like the thing is clear. Chlorine is going to have the most charge. Chlorine's charge is going to be greater than chlorine's charge. But what about the distance? So give it a like thought for a few seconds. Let me plug in my charger. What should be the case? What should be the reason?
Sir, the
Right, tell me.
sir, the displacement is higher for
Yes,
chlorine.
yes. It is exceptionally high. For example, you can see the answer here. The ideal dipole moment is this. As we are going from fluorine to iodine, the dipole moment is decreasing. But for this specific case, here we are observing this exception sort of thing. This reason is, in case of CH3Cl, the length of CCl, the length of this CCl bond is exceptionally higher than that of CF, and that contributes to its higher dipole moment. For example, if the CH3Cl look like this, then the CH3F look like this, then the CH3Cl will look like this. And if we have to calculate the dipole moment, we need both factor, right? For
Sir.
example, we are accepting the fact that the charge on this fluorine is going to be higher. For example, it is 20 and here it is 15, right?
Yes, sir.
CH3F. If you have to calculate the dipole moment, then it is charge into displacement. The displacement here is 10, but the displacement here is how much? For example, it is 25,
50.
25, right?
Yes, sir.
So if I have to calculate the dipole moment for this, it is going to be 20 into 10, it is 200, but the charge is less, but the displacement is exceptionally higher. So the value should be greater than 200, right?
Yes, sir.
So that's the reason. Is this clear?
Yes, sir.
So let us jump to the main topic now. So as the chapter's name is Haloalkenes. So we are going to divide it into three parts. First, we are going to see how we can prepare the haloalkanes. We will see different methods. We will see different initial substances, like we can create haloalkane from alcohols. We can create haloalkane from alkanes. We can create haloalkane from allylic halogenation, from alkenes, alkynes, right? From different starting reagent, we can calculate haloalkane. So the first part we are going to deal with is how to prepare haloalkanes, right? For this, the first case is from alcohols. We can produce haloalkanes with the help of alcohols, right? So the first method is by reacting it with HX, by reacting it with HX in presence of by reacting it with HX, HX could be HCl, HBr, right? In presence of Lewis acid, which is ZnCl2. And this is what Lucas reagent test as well. Okay, just give me a second. Try to give it a read for a few minutes, then I will explain. Just give it a read. Just see what's happening, which type of alcohol we are using. And for organic chemistry, I would request you to please revise. As long as like the moment class is over, try to revise it. Otherwise, you will find it very hard. Organic chemistry is all about revision and revising, right? If you know one concept, you will be able to answer the next one. If you miss any single concept, your whole organic chemistry will go downhill. It is all about basic. If you know A, then only you will be able to know B. Otherwise, so you can study any chapter, but you have to study organic from the starting, because the things that we are going to learn here, it is going to be used in the next chapter, alcohols. The thing you will learn in alcohol, it will be used in aldehyde. The thing that you will learn in aldehyde, that will be used in amines. So it is all connected, right? So let us see what is happening. We have fixed what? Our main goal is to prepare haloalkane. And the first case is we are talking about how we can create haloalkane from alcohols. So our starting reagent is fixed, which is alcohol. We are changing the attacking reagent. For the first case, we are using HX. It could be HCl. It could be HBr, right?
Yes, sir.
And we are using Lewis acid, which is ZnCl2. And we are getting what? Our required or desired product, which is haloalkane or not. And
Yes,
elimination of
sir.
water is taking place. Is it clear what I just said?
Yes, sir.
Now let us understand the mechanism. We will talk about the mechanism, right? First of all, let us understand what is Lucas reagent. The Lucas reagent is the mixture of HCl plus ZnCl2. If you are mixing concentrated HCl with ZnCl2, it is called Lucas reagent. And this Lucas reagent is very useful to differentiate between 1 degree, 2 degree, and 3 degree alcohol. Suppose in your practical exam, your teacher is asking, suppose they have given you a test tube, and inside the test tube, they have mentioned it contains alcohol, and they are asking whether this alcohol is 1 degree alcohol, whether this alcohol is 2 degree alcohol, or 3 degree alcohol. So how can you differentiate? You can differentiate it with the help of Lucas reagent test, right? So what are you going to do? First of all, whatever you don't know which type of alcohol you are having in your test tube, you will transfer concentrated HCl and you will add ZnCl2. This turbidity. What does this turbidity means? Turbidity means you will see a formation of milkiness or cloudiness in your test tube. You will see some whitish type of clouds in your test tube, right? That means turbidity. If that turbidity is happening around half hour, like you have transferred your reagent and after 1 or half hour you are observing this cloudiness in your test tube, then you will say this alcohol is.
Degree.
And if after transferring your Lucas reagent you are observing the turbidity in 5 to 10 minutes, you will call it, or you will
2
say this
degree alcohol.
2-degree alcohol. But if you are getting the turbidity instantly, then you will say that this is 3-degree alcohol, right?
Yes, sir.
So with the help of Lucas reagent, you can differentiate the 1-degree, 2-degree, and 3-degree carbohydrate. Is this clear? This was our first preparation method of alcohol, and we have to talk about several of them.
Yes, sir.
Right? So what we can conclude from here? The reactivity order of alcohol is what? Which one is reacting fastest?
3 degree.
3-degree, then 2-degree, then 1-degree, right?
Yes, sir.
For 3-degree alcohol, we don't even need the ZnCl2. This ZnCl2 is what? This is a Lewis acid, or you can say catalyst. It is helping the reaction to go faster. But if you are having 3-degree carbocation, or sorry, 3-degree alcohol, even without the help of ZnCl2, you can do the reaction. And we will talk about it while dealing with the mechanism, right? For now, it might sound very typical for you, right? Because we haven't dealt with SN1 or SN2. These SN1 and SN2 are specific mechanism that we are going to deal with as we move ahead with the chapter. But for now, try to understand. You don't have to think about it that deeply, but if you are having any simple doubts, I can answer. Otherwise, in SN1 and SN2 mechanism, we will talk about it in details, right? There, all of your doubts will be clear. For now, let us understand what is happening, like the mechanism, right? If you are
Yes, sir.
taking 1-degree alcohol, if you are taking 1-degree alcohol, right? The HCl is what? HCl is basically acid. What's the main purpose of acid?
Sir, catalyst.
Acid, basically. HCl is an acid. The main purpose of an acid, of any acid, is to provide H positive. If something is providing H positive easily, then it is a strong acid, right? The acid main purpose in life is to provide H positive. So if I am having HCl, then I have abundance of H positive, right?
Yes, sir.
Now, on oxygen, we have two lone pairs or not?
Yes, sir.
And this is electron deficient thing, like H positive is electron deficient, and this lone pair is electron rich, right?
Yes, sir.
So this OH group will attack on H positive. This will attack on H positive. One more thing, the arrow is always going to be from high density to low density, right? So the high density is this O lone pair and this low density is H positive. So the arrow is from lone pair to H positive. So what it is doing? Due to its lone pair, it is picking up this H positive from the reaction and it is attaching it to itself. What is it doing? It is picking up this H positive from the reaction and it is attaching to itself. Now, to help this H positive, it is utilizing its own lone pair, right? It is utilizing its own lone pair. Ideally, the oxygen should have two lone pair, and now it has used one lone pair to help what?
Chlorine.
Which one? See. Let me take a
It used
different.
one lone pair to bond.
Donate what? To help which atom out of H positive or chlorine? Which one?
Sir, H positive.
Good. Now, because it has tried to help some other person, so the positive charge on H positive H is transferred to what? O positive. The positive charge on hydrogen is transferred from H to O. Why? Because oxygen tried to help H. So if it is donating its own lone pair, then the positive charge will transfer. Now, oxygen is very electronegative, right?
Yes, sir.
Oxygen is one of the most electronegative element. These three are most electronegative elements, right? Fluorine, oxygen, and nitrogen. So if you have abstracted electrons from a electronegative species, you have taken money from a person who is very what you will say uh money conscious, right? You have taken money from some person who is very money conscious. Like he will be very undisturbed, right?
Yes,
He
sir.
will become very unstable. So the moment oxygen bears a plus charge, it will try to neutralize this plus charge. So for that, there are two possibilities. Either it could use SN1 method, SN1 approach, SN1 mechanism, or either it could go from SN2. So for now, you can understand SN1 as whenever we are talking about SN1 mechanism, we will always see the formation of carbocation. What is carbocation? A carbon with a positive charge. For now,
Yes,
what you
sir.
can understand? Whenever we talk about SN1, we will observe self-ionization. This oxygen will do what? This oxygen will take these two electrons and leave from the compound. Like it will leave this alkyl chain by taking these two electrons. If it is taking these two electrons, then there will be a positive charge on the carbon because the carbon's bond has been taken away from oxygen, right? So it will bear the positive charge. So what we are seeing, initially the positive charge was on hydrogen because oxygen tried to help it. The positive charge transferred from hydrogen to oxygen. Now, to stabilize its own charge, it took electron from carbon. Then now at the end, the positive charge is where? At the carbon. Is it clear till here?
Yes, sir.
Now 1 degree carbocation is very unstable. Why? Because there are not many groups which can donate electron density. Here we have only, have you heard about hyperconjugation?
No, sir.
No.
No, sir.
Yeah. Okay. See. This is what? A carbocation, and to be specific, 1 degree carbocation.
Yes, sir.
Okay. Now, this is what? A carbocation, but 2 degree
Degree.
carbocation. This is 3 degree carbocation, right?
Yes, sir.
All of them are carbocation, but they are different in primary, tertiary, and secondary part. Now, have you heard about inductive effect plus I minus I?
Yes, sir.
Okay. So we know methyl group can act as plus I. It can donate electron density.
Yes, sir.
So if we have a positive charge to stabilize it, its neighbor, it's donating its own electron density. Suppose you have your friend and you are in shortage of money and you are asking your friend to lend some money to you, right? So you are basically doing what? You are trying to stabilize yourself by taking help from some other person, right? From your
Yes, sir.
neighbor. So here we have only one neighbor for it. So the electron donation is only, like we are observing, only plus I, only one plus I, right?
Yes, sir.
But for 2 degree carbocation, how many groups or how many neighbors does it have?
Mhm.
Two. So rather than having one friend, it has two friends. So both of them are helping him by giving some of their own money by plus I. Here he have three friends, so they are giving money again. So out of these three, which carbocation should be the most stable?
The 3 degree carbocation.
Why? Because it has three friends which are trying to help him. And in 2 degree, it have only two, and for 1 degree, it has only one. So the most unstable carbocation is 1 degree carbocation. 3 degree most stable, then 2 degree, and then 1 degree. Right?
Yes, sir.
Now, let me tell you about the hyperconjugation as well. Suppose the plus I part is clear.
Yes, sir.
Now, this is alpha position. The
Yes, sir.
next carbon to the carbocation is alpha position, right? Give me a second.
Sir.
Here, this is our main site. To this is directly attached and this is directly attached. It has two alpha position, two alpha carbons, right?
Yes, sir.
Here, how many alpha carbons do we have?
3.
Three.
3.
So here we have how many alpha hydrogens? To this carbon, how many hydrogens do we have?
2.
So here we have two alpha hydrogen. Here,
5.
and for this,
8.
8. Great. So the more the number of alpha hydrogen, the more will be the hyperconjugation. Similar to our inductive effect, hyperconjugation helps us to stabilize the carbocation. So the hyperconjugation, similar to inductive effect, is most for 3 degree carbocation. So due to hyperconjugation and inductive effect, our 3 degree carbocation is most stable and 1 degree is least stable. So here, which type of carbocation we are observing? 1 degree. So it is very unstable, right?
Yes, sir.
So what will happen? I will give you a scenario. What is actually happening while we are seeing these reactions now? All of this is happening inside a liquid medium, right? Try to imagine it in this way. You have alcohol, which is in liquid form, right? You have
Yes,
added some
sir.
HCl into it, which is also in liquid form. The moment HCl goes into the aqueous solution, it breaks down into H positive and Cl negative. Is it making sense till now? Suppose you have a
Sir.
beaker, you have alcohol inside it, and you have added HCl. The moment you add HCl, the HCl will break down into H positive and Cl negative. Why? Because solvation is happening. Because in aqueous medium, they will broke down into something and they will get isolated, right? Basically. So now we have excess of H positive and excess of Cl negative. This alcohol will see those H positive and try to help them by donating its electron density. Due to this, we have this whole consequences, right? Now, we have SN1 mechanism. For SN1 mechanism, what I told you, we will see a carbocation. For SN2, what will happen? For SN2, they will not make carbocation. It will be a simultaneous process. For example, for today's class, I know it might not be making much of sense, right? Is it making sense or not?
Yes, sir.
Are you sure? Because we haven't talked about SN1 and SN2, so this must be very typical.
Sir.
Once we are done with this chapter now, and then try to look at this stuff. This will be like child's play for you for now, because in NCRT they have gone with this approach, so we have to follow it. If I am talking about SN2, we are not trying to form this carbocation. What will happen? The this nucleophile will come and attack at this carbon, and simultaneously this H2O will leave, right? So we will observe
Yes,
this.
sir.
So from here, we cannot make SN1. Through SN1, we can not make a desired product. By SN2, we can make. But this is very slow. It could take days, and under mild condition, it might even not form. So if I'm taking only HCl, if I'm not taking ZnCl2, the reaction can proceed by SN2 mechanism, but it will take like 4 or 5 days. Or if you are not heating it, it might even not occur. So to avoid this, what we are using? We are using this ZnCl2. With the help of ZnCl2, what is happening? Instead of attacking H positive, it is making a complex. It is making this type of complex, and this is doing what? This is enhancing the reactivity. How? Because it is creating much more polarity in the bond, right? So now, if this chlorine, this is nucleophile, right? If
Yes,
this
sir.
chlorine had a tendency of 10 rupees, if this chlorine had a tendency of 10, in case of where we were not using our ZnCl2, but if we are using ZnCl2, this site is even more electropositive. So this negative charge will be more attracted toward itself to this
Yes,
carbon
sir.
site. So if initially it had a tendency to attack it with 10, like 10 basically, now it has a tendency to attack it with 20 force. So now it will go there faster. So the reaction will occur a bit faster, right? So you might observe this reaction in an hour or two or 30 minutes, depending on the length of the chain. Right. So Lucas reagent is doing what? If they ask you what is the purpose of Lucas reagent, what you can tell? ZnCl2 is crucial not just to speed up the reaction, but to make the reaction occur under mild condition by activating the OH group and stabilizing the transition state. Is it clear why we are using ZnCl2? Because without it, the reaction may take 2 or 3 days,
Sir.
and it is forming a complex basically. Is it clear? You can ask me like 20 times, I don't care, but try to understand, because if you are not able to understand the first chapter of organic chemistry, the rest will not make sense. Ask as many times as you want.
So ZnCl2 is the catalyst.
Yes, it is a Lewis acid, a catalyst basically.
Yes, yes.
This SN2 and SN1 part, you can leave it. I will explain it in detail, right? We will take several examples. Rest,
Yes.
if you are having doubt, you can ask.
So,
For 2 degree, what will be the case? Now, again, this will attack on the ZnCl2, right? This will form this complex, and if I am having 2 degree carbocation, generally we will go through SN1 mechanism. If I am talking about SN1, for now you can understand it. If I am talking about SN1, I will always observe the formation of carbocation. These two bonds, sorry, these two electrons in this single bond will be taken away from oxygen to stabilize its own positive charge, and it will leave a positive charge on carbocation, sorry, carbon. So this is positive side, right? And in our reaction, we have Cl negative. So this will act as a nucleophile and attack at where? This positive side, and it will form our desired product, right?
sir.
Similarly, in 3 degree. In 3 degree, if you are using ZnCl2, it is good. If you are not using it, again, it is good. Why? Because in 3 degree, the carbocation is which one?
Degree carbocation.
And 3 degree carbocations are most stable.
Yes, sir. Yes.
So that's why even without ZnCl2, you can proceed with this reaction because our carbocation is 3 degree carbocation. Now a question for you. If 3 degree carbocation is most stable, if 3 degree carbocation is most stable, then why it is reacting at the first place? A stable thing should not react with something else, right? So why this is reacting and why 1 degree is not reacting? Try to think about it for a few seconds. If 3 degree carbocation, if 3 degree carbocation is more stable, then why it is reacting? And if 1 degree is not stable, then why it is not reacting? It should react with something and get stabilized now. So why this is not happening? Try to think about it. Okay. Why should 3-degree carbocation react if it is the most stable intermediate? If you are not able to answer, you can tell me. We will discuss about it, right?
Yes, sir.
Suppose all of these reactions are happening where? In liquid state. Suppose you are inside a pool, right? Your pool is what? A solvent. You are inside a pool and that pool is your solvent. It could be acidic. Suppose the pool is consisting of HCl. In that pool,
Yes,
you
sir.
have H positive and Cl negative ions. Now, you are alcohol. You are alcohol, right? And there is some other person which is what? Your attacking reagent or nucleophile. For example, here we have Cl negative as nucleophile, right? Cl negative is our nucleophile.
So,
Now, the first thing you as a alcohol or as a substrate, I will tell you what are substrate and what are attacking reagent after this. For now, you can understand it. What a substrate is a thing where the attacking reagent is attacking. The side that is getting attacked is substrate. So here, alcohol is our substrate. Okay, all
yes,
of
sir.
you are inside a pool. The first thing that you will do is you will pick a H positive from that pool, right? You will do what? You will say like I am a stable person and I would like to help some poor person. And the poor person is what? A poor person in that pool is H positive. So you will try to help that person. You will give your own electron pair and you will try to help it. But the moment you give your electron pair, you will bear a positive charge. And now you are very unstable. So the moment you bear a positive charge, you will do what? You will say like you will ask your friend to give you some money. So you will take the two electrons from which is connected directly to you, carbon. You will take carbon's electron bonds and you will leave carbon with positive charge, right? Now, which is in trouble? Which species is in trouble? Carbon one, carbocation.
Yes, sir.
Is it making sense?
Sir.
Are you sure?
Yes, sir.
Now, suppose you have formed a 1-degree carbocation. Your 1-degree carbocation is what? Your 1-degree carbocation is the site where this Cl negative is going to attack, right? It is the substrate. The Cl negative is going to attack at the C positive charge or not.
Yes, sir.
Now, the important thing is suppose if you are unstable, if this 1-degree carbocation is unstable, then it will be formed for very few seconds. It will be formed for very few seconds and it will disappear or it will convert back into the its initial stage. Suppose this carbocation is very unstable, so it will do what? It will take the H2O again and it will give back what? This alcohol. So the moment this 1-degree carbocation is forming, due to instability, it will remain in its 1-degree carbocation form for very few seconds and it will convert back into what? Its initial stage, which is alcohol. This process will occur very fast. So the carbocation that you are getting is for very few minutes or few seconds, right? Even nanoseconds. So inside that pool, if the chlorine needs to attack at some place, if the chlorine needs to attack at substrate, that substrate should exist for some time now. Suppose suppose look at the screen. This is your beaker. Inside this beaker, what you are having? Suppose after some time, you have formed this carbocation and this chlorine negative is here. If this chlorine negative have to attack at this substrate, which is what? Your carbocation, 1-degree carbocation, which is formed by alcohol. So this chlorine needs to travel in that liquid medium and try to reach it, and it will take some time, right? From A point to B point, if it need to travel, it will take some time. But this
Yes, sir.
1-degree carbocation, due to very instability, it will exist for very few seconds. So the moment this chlorine see this 1-degree carbocation, and the moment it will reach the place from where it can attack, the 1-degree carbocation won't exist. So if there is nothing, so where this chlorine can attack? No way, right? Is it making sense? I am trying as
Yes,
best
sir.
as possible. So due to the instability, the carbocation is not present for a very long period of time. So the moment the chlorine reaches the site to attack, the site will no longer remain, right? So that's why 1 degree carbocations won't lead to the formation of 1 degree haloalkenes. On the other hand, if I am talking about this 3 degree carbocation, in the reaction, this 3 degree carbocation can sustain for some period of time. What I'm saying, inside this pool, if I am having 3 degree carbocation, right? This
Yes,
can
sir.
sustain itself for some period of time. So it can sustain till this chlorine reaches this point. It can sustain itself till this chlorine reaches this point, and it can sustain till it can attack at this point, right? So 3 degree carbocation is stable, and hence it can stay longer inside our reaction, and it can allow the chlorine to reach itself and get attacked. So that's why we will observe the formation of haloalkane, right? Is it clear?
Yes, sir.
Are you sure? Because this is a very like not understandable concept by students. Like students find it very hard to understand why 3 degree carbocation is unstable even though it is reacting. I hope it is clear now. If you have any doubt, you can ask.
Sir,
Because the
the
thing,
one degree,
mhm.
sir, the 1 degree carbon will not, sir, it will not react because it will be present only for like some time. That's why. But the
Very
three
few
degree,
seconds.
yeah,
Uh,
but the 3 degree will stay for a longer time. That's why it will be, yeah.
it will be attacked. It will be able to get attacked, right? And if
Yes,
the
sir.
nucleophile attacking, then only the product formation will occur, right? That's the
Yes.
reason.
Okay.
So this was about our first method, right? Again, this mechanism for now, just try to give it an overview. After we are done with the SN1 and SN2, you will automatically see and understand it. You will like see it as ABCD. So let us talk about the second preparation method. First, we have prepared haloalkane with the help of alcohol, and the reagents were HCl and ZnCl2. Now we are doing what? Our starting reagent is same. This is our substrate. The thing which is getting attacked is what?
Substrate.
Substrate. The thing which is attacking is what? Attacking reagent, right? So now the second method is you are reacting alcohol with NaBr in presence of H2SO4, and you are getting, again, this is haloalkane. The side products are NaHSO4 and H2O, right? You can
Yes,
use
sir.
NaBr and H2SO4, or you can use directly HBr. In your NCRT, they have gone through this approach. So try to write it like this. This NaBr and H2SO4 after some time are basically getting converted into HBr, but you can write it like this. This is your second method of preparation. Now, from here, what we can see, suppose if I am only using NaBr, if I am not using H2SO4, what is going to happen? If I am only using NaBr, the reaction won't proceed. Why? Because the leaving group. Have you heard about leaving group? What is leaving group? This is
Which
again
will be
11th
formed.
basic. Okay. What's leaving group?
It will be formed with the product.
Good. A leaving group should be what? A good leaving group. And what is a good leaving group?
A strong base, no, a weak base.
A weak base is a good leaving group, right?
Yes, sir.
Okay, okay. So here, what is happening? If we are going without the help of H2SO4, if we are doing this reaction in absence of acidic environment, then our leaving group is going to be what? NaOH, which is a strong base, and it is a weak leaving group. So what does a weak leaving group do? Suppose. Here, I have to remove OH. I have to remove OH, and if I am removing OH, it is getting removed in the form of sodium hydroxide. And this sodium hydroxide is a strong leaving group, or sorry, strong base, weak leaving group. So a strong base will do what? It will try to again attack at the substrate. The moment it is formed, it will try to attack at the substrate again, and it will form our starting reagent again. So here we won't be able to form our desired product. You can understand it this way. I will use Urdu for this. Suppose if we have to kick out someone, if we have to kick out someone from a room, right? That person should be weak. If I am kicking someone out from a room, that person should be weak. Otherwise, it will break break the door, or like he will basically come again in the room, right? If he is strong, then he will break the door and he will be back. So if I have to kick out someone, he should be what? Weak. And by weak, I mean weak base. And if it is a weak base, it is a good living group. So if somehow we are eliminating a species which is strong base, then it will again attack back and give us the same product. So we will avoid a reaction where the leaving group is strong base. Is it making sense?
Yes, sir.
So what should be our priority? We have to convert this strong base or weak leaving group into something which is good leaving group. So for this, we are reacting it with in presence of H2SO4. In presence of H2SO4, the leaving group will be H2O. And H2O is a weak base and good leaving group. So let us understand how it is happening. Again, this OH is having electron density. It will pick what? H positive from the reaction.
Yes, sir.
Then it will convert into what? It will, the positive charge on H positive is now on O positive. Why? Because it tried to help H positive. And because because oxygen is electronegative, a positive charge on oxygen is very unstable. So the moment the positive charge is uh, formed on the O positive, it will try to neutralize it by what? By taking electrons from other. So it will take the electron from the neighboring bond, right? And simultaneously, this bromine will attack. This is SN2. We will talk about it in detail after some time. This will come, this will attack here, and simultaneously H2O will leave, and we will get our desired product. Here the leaving group is what? H2O, and hence this reaction can proceed. Is it clear?
Yes, sir.
So this is our second method. Again, a question from your NCRT. Why H2SO4 is not used during the reaction of alcohols with Ki? The question is, if you are reacting alcohol with Ki, why you are not using H2SO4 as your solvent? The answer is H2SO4 is a strong oxidizing agent. Right? Try to understand it. H2 is not using okay, because it's oxidized. Let me write it. See, try to look at this. In our reaction, suppose I have alcohol and I have Ki. Right? What I told you, if I am transferring Ki into an aqueous solution in a liquid state, then this Ki will be broken into K positive and I negative, right?
Yes, sir.
In the liquid state, like NaCl in water is present in like how it is present in water in Na positive and Cl negative ion, right?
Yes, sir.
Similarly, Ki similar to NaCl will be present in water or aqueous medium like K positive and I negative. So this Ki actually looks like this, right? Out of these two, this I negative is supposed to act as nucleophile. But but if I am using H2SO4, if I am using H2SO4, this I negative will be converted into Hi, and then further it will be converted into I2. So Due to the presence of H2SO4, our desired nucleophile is converting into something which can no longer act as a nucleophile. So that's why we try to avoid using H2SO4 because it is a strong oxidizing agent. It converts our ideal nucleophile, which is I negative, into I2, which is not a good nucleophile. If we are not having a good nucleophile, then the reaction cannot proceed, because if we need to proceed the reaction, nucleophile has to attack somewhere, right? And
Yes,
get
sir.
itself attached. So why we don't use H2SO4 as a medium while preparing this? The reason should be H2SO4 is a strong oxidizing agent. And in the place of H2SO4, what we use? H3PO4. Is it clear?
Yes, sir. Yes, sir.
Right. Give me just, okay. Okay, we will discuss this in the next class. Right. For
Yes, sir.
now, one more thing that I would like to tell you is, see, your exam is on 16th, right? So you have to work a bit hard because I don't want to rush anything about this chapter because this is the basic of 12th organic chemistry. So it will take some time to complete it. So for that, I have one thing that can help you is, see, if you are preparing for your exam, right, you are supposed to solve NCERT questions because in organic chemistry, they won't ask you anything apart from your NCERT. They will ask you very limited question and that too from your NCERT. This is short notes. This is for what? Once your board's exam will be near, you will have to learn from these only. But to understand this, you need to thoroughly know about the chapter, like what type of reaction is happening, why this is happening, right? Once you have done
Yes,
your
sir.
chapter thoroughly, then you will just have to go through this 10 pages more and you will be able to understand the entire chapter. So for now, as your exam is near, I would request you to go through this short notes and read these short notes. These are only 10 pages. And after this, try to do the NCERT questions. In this, in these 10 pages, you have every possible question that they might ask you in your